We now give a look to the attention model at work. We see how the model introduced in the Badenau and others attention paper. We give a look at how the model behaves and at the improvement in performance that it allowed to achieve. First of all, we find in the paper interesting insights on how does the model, the attention model behaves. And here we see in French to English translation, what does the attention model perceive as most relevant input symbols for each output symbol, and they are shown with a clearer, with a whiter color. So most of the times we have a word-by-word correlation, like for this signed word, and in other occasion we can see that since the order of the words is reversed, we see here that this diagonal in the other sense with respect to the natural progressing of the words takes into account. And in other occasions we see that we have areas where the link is not exactly word by word, but we have groups of words that are considered and translated together. Here we see two more examples, also presented in the paper, where we can see that the man said, which is an expression that it's not exactly translated word by word in French, gives a series of English words that somehow, for translation, pay attention to these three input word, as we can see in this clear area in this position. And performance-wise, the model presented in the paper was a success. The performance for machine translation algorithms are measured using a scoring mechanism called BLUE, and BLUE is based on some reference human translations that are considered the golden standard, and the translation which is produced by the model is scored using the presence of expected words in the translation, which means words that are part of the golden standard. And also we measure and we give points to sequences that are produced of 2, 3, or 4 words that are also that are predicted and are also part of the target sentences. Anyway, we see that this scoring mechanism is used, and the proposed model, which is an encoder decoder plus attention, is compared with a similar model but without the attention module, which is RNN encodec. And the main scoring is performed with sentences of two lengths, which are 30 words and 50 words. And we can see that the performance of the RNN search model, which is the model with attention, are better, and the improvement increases with the length of the phrase, which is not a surprise, knowing what are the pitfalls that attention solve. So here in the lower left, we have an interesting graph that for four cases, so we have both the new model with attention on 50 and 30 and the old model also on 50 and 30. We see the performance as the real length of the test sentence increase. And we see that the RNN search model with attention on 50 words of these models is the only one that it's very consistent, very constant in its performance, even when the phrase is more than 30, more than 40, and more than 50 words long. We can see here an example of translated sentence, and for this sentence we have the English source, and we have the translation with the old encoder-decoder model, and we also have the translation with attention. And since for those lucky ones who speaks French, will be much easier than for us, but we see that the old model is not doing very good, because we can see that the open quotes are not closed, and we see that the phrase is much shorter, and it's missing the last part. So if we look at the reference and we compare to the sentence generated by the attention model, we can see, even if we don't understand the French that well, that the sentence is much more complete, and it also has the enclosing quotes, and the sentence is close to both to the reference and to the Google Translate results. As an afterthought, we can say that the performance of attention should not be surprising, because if we think about how humans listen to sentence, read sentence, and understand especially long phrases and work on translating them, we realize that we don't process text in sequences. When we listen to a sentence, the sensorial memory is keeping large range of what we listen to, and if we look at how professional translator work, they read the source back and forth, they highlight word, in other words, they work on the input that they must process, not one symbol at a time, but looking at all of it, and especially at different moment, looking at what is the most important parts, what are the most important parts of it for the part of the translation that they are generating at the moment. As final topic, we now try to look at a more general view of attention, which can be useful if we want to dig into later developments of technologies and on later models such as transformer, BERT, and so on. Let's imagine we are working on a problem. We have some data that we are processing and from which we want to derive some processing, some output, some information. Okay, so we call these data, we call them query. And the query, we can assume that, as always, is a vector. So we are working on vectors of data. And what we think, what we envision, is the possibility to have some additional data that we call context, that could help us, that would be helpful in processing this query, so that the results that we are going to obtain can be better given by processing the query and the context together. To find how we can obtain the content for this context that we don't have yet, we know that we have some kind of database or knowledge base or set of pieces of information, that we know contain useful data that could help us in building our context for our query. The repository of information where we are going to look to find the good content for our context is organized in a way that for each piece of information that we call value, there is also a connected piece of information that is the corresponding key. And the objective of the key is that the key is able to tell us how relevant is this value with respect of the current problem that we have, the current information that we are processing, that is the query. So somehow we can make the query interact with all of the keys, and for each key we are able to derive a score that tells us how relevant is this value for this query, how helpful is this value in processing the query. So how much of this value should we go take and use to build our context. And here in the example, we see that the first one is not very relevant, the second one is the most important, and also the third is fairly meaningful. The second step is quite simple and should remind us of something that we have already seen. We simply take these values that are the scores and we normalize them. We basically put it in a more useful way, so they are now a probability distribution, and we see that the total of all these values is 1. Now that we have this probability distribution, what we can do is that we can use these weights to select each of the values in a proportion that is similar to its own weight. So we are going to take 0.1 of this value, 0.7 of the orange value, and 0.2 of the green value, so that we give the proper balance to the value, and we are so able to build our context in the most meaningful way. Just to recap, the query is the problem at hand, the piece of information that we are processing. The values are the data that could help us in processing the query, and the keys are, for each of the values, the information and the data that reacting with the query can tell us which one of the values are the more useful and more relevant. So if we look at how attention was introduced before, we see that in formula number 1, we have the query, which is the previous state. And we make the previous state somehow react with all of the keys. And the encoder states were the keys that allow us to calculate the scores. Then we normalized the scores as attention weights, and then we could use these weights alpha to select a weighted sum of the values. And again, we have Hj here, so that in the model we saw the values and the keys are same vectors. And we can look at this as a particular case. In this case, values and keys were the same, but in a general understanding, in a general acception of attention, keys and values may differ. And when we go fishing among the values to look for relevant information, we do something similar to what we do when we do a search in a database, because we could look at our values as rows on a table, and we could look as keys as, of course, keys for each of the row. So if we think of the query as some kind of selection criteria, we can use the query on the keys, and typically what we may get in database query is one row when we have some set of keys here that match the query criteria. The results for attention is not as crisp, but we may say that we have a kind of fuzzy results, because here we have that we take, for example, this row with weight 1. So we take all of it and we take nothing from the other rows. In case of attention, what we get is a more smooth selection, where we can say, okay, I take 0.2 of this row, I take 0.3 of this row, and I take 0.5 of this row. So there is an analogy between attention and a database query, and you can look here in the table where there are several aspects that are compared, and of course in the database we have a query key matching, and it's based on rule-based logic, while in attention mechanism we have a similarity score between the query and the keys. And if you look at what the query returns, we see that in databases a row, a record is returned or is not. So we return only the records matching the rules. In attention, the logic is more fuzzy. We return a probabilistic estimate of all the records in our database. That finishes our discussion, and you find here the main references that were used for the presentation. Most of the references are also in the single slides where they were used, but you can look also at this final list as a recap. We hope this discussion has been interesting and useful, and if you have gone so far, we thank you very much.